Doom music's hitting too hard. It's only playing for me. Okay, so last time we did this, we looked at the setters and getters, which are decorators in Python. They're nice to use in object-oriented programming. And there's also a deleter that goes along with the setters and getters. We looked at building our own custom decorator, but did not do it on an object or on a method inside of a class. So I want to revisit that. So today, at some point, we're going to revisit that. So decorate a method. And I just kind of want to do that for like debugging. I think it would be kind of convenient. And then, yeah, so we're going to revisit this. And we definitely looked at the class property decorator. Yeah. Okay. And prior to that, we reviewed OOP. Now, I may take a look at some LeetCode problems if I'm just kind of hanging out here. And I have a couple that I can look up that aren't too bad. Like I've worked through them before, and I'll probably revisit them. Maybe turn those into videos where I solve the problem. And then maybe, just maybe, take a look at Apache Beam. It's something I want to learn, and we can do it. They have some examples, so we can do Apache Beam examples from the documentation. And in order to do that, we would have to install it. We don't have it running in here, so I believe it would be Apache Beam GCP version is what I would install. That's probably good. Let's see if that works. And I'm inside of a container here, so this is going to modify my container, but it's not actually modifying the... Actually, I'm not inside my container. That was a lie. Where's my container? There we go. Okay, so this should all be the same. Yeah. Okay, so we have our volume shared. So we can get out of here. And if we want to do Jupyter Notebooks, we can do it with this. That is not the right one. There we go. Look at this hideous. Okay, you got to go to settings and theme, dark mode. Okay, so if we're going to play around with Apache Beam, we probably want to do it in here, in a notebook. It just makes life a lot easier. Okay. And we don't even, this has my notebook server, so I want to leave this open, but I need to get to the other one. Okay, so this is inside of a Docker container, so whatever I install in here, like, it just really doesn't matter. Okay, so this is going to install Apache Beam, so later on we can take a look at that. A lot of stuff going on there. Looks like it worked. And then we could, of course, try it. Maybe it's import Beam. Let's go take a quick look. Was just playing around with some of this stuff. So I have an example somewhere. Just a question of where. Oh, it's import Apache Beam as Beam. Okay, that's easy enough. Okay, so the install did work. This will be here later. But first, I want to take a look at, let's go find an example of a decorator inside an object. Grab this thing. So we've got a little class, or a little Stack Overflow instead of ChatGPT, although that would work out well. That'd probably give us a good example too. So it looks like they're using self as part of the decorator. Except for this is the, I mean, this is the not the code example, so this is the way it goes. Yeah, so they're not using self. But let's just run this and just see where that takes us. So they're defining the decorator inside of the class. It does not have a self. It's just saying foo, which is kind of weird because this would normally be self just by default. But maybe when you decorate something, like this is not a static method. Let's kind of look at another. Let's keep looking. So def magic self, print start magic, foo, calling it with self. It's kind of interesting. So magic is the thing that's being wrapped around the function, and foo is the function that gets passed in when you decorate it. How old is this? This looks pretty old. (2018). It's a little sus with this. It's Python 2 because of the print statements. So still, see, this is not the, so they're decorating it by passing it in as a function. They're using self like inside the class. That's really weird. What we're wanting to do is not possible. It takes, for instance, whether or not the code below looks valid. Of course, isn't valid because self isn't defined at that point. Yeah, of course, that doesn't work. Need class level access, try this. So they're doing CLS on the decorator, and that's where I thought it would need self defined. I don't need class level access though. I want access to the instance. Like I want to decorate a method that has an instance. This uses func tools to wrap. Wrapper func def wrap self args kw args inside wrap. Func passes the self. This kind of looks promising. I want to try this one. We don't want to do it in here. We want to do it in VS Code. So let's make a little method decorator.py. Let's drop this stuff in here. So we're going to use func tools wraps. And since we're using something, let's go take a look at what this is. We could probably just mouse over it here. Decorator factory to apply update wrapper to a wrapper function. Returns a decorator that invokes update wrapper with the decorated function as the wrapper argument and the arguments to wraps. as the remaining arguments. Default arguments are as for update wrapper. This is a convenience function to simply apply partial to update wrapper. None of that makes sense. Okay. Let's see. Wrapper is going to take in, like, func should just be this method. Func tools wraps. So we're using a decorator on this, and then wraps. And then you get self args, kw args. And then we're going to try this just with this generic method. And say after func call. Maybe before func call here. Okay, and then we just want to return whatever that output is. Okay. And maybe do a little bit of formatting, maybe a little saving. It's yelling at us here. Argument 1 to wrapper has incompatible type callable. Expected example. Wrapper has incompatible type callable. Example any. Expected example. I'm going to run this anyway. I mean, that's just like a MyPy thing. Okay, so, I mean, it ran. So we have something happening before the func call. We have the method, which is being printed out here inside the method. And then we have the after func call. Let's do a little bit more stuff here, I guess. I just want to like define some stuff inside of this instance and then try to access it within our function and see if that works inside the decorator and all that stuff. It's just like, I don't see any reason why it wouldn't because it already successfully ran. And we don't want to do it here, but we do want it here. So that way, because we didn't access the self, we didn't access, like this is a method, but it's not actually making use of self here. And now we can check some x and y values just to see what those are like. And maybe since now we're trying to access self, the thing that gets passed in from the wrapper is going to break. Is the only reason I want to check this. And we run that again. We got to make it an F string, so that doesn't look quite right. Thank you for the like out there. Appreciate it. So this is working. So now we have a decorator, but it has to be defined within our class, which is honestly kind of annoying. So what I want to do is probably inherit this thing. Like this works. There is a problem here. Argument 1 to wrapper has incompatible type, but this is a warning. This isn't really expected. So wrapper has the incompatible type. We're expecting it to be example. So, I mean, maybe, and that can't possibly be right. No, that doesn't fix it. But it works. It's just like there's something in the formatting that is ugly. We're just getting this warning. It's not an actual error. But what I want to do is I want to put this thing into its own class and then inherit the class and maybe just call it like debug. and then just try to make it something useful. And now, in this example, like if I wanted to debug in here, I could inherit debug and then wrap it. Oh, okay. Oh, it is a static method. Okay. That's kind of... So wrapper equals static method wrap it. I wonder if we can just do another decorator instead of this down here. I think I'm trying too many things at once now at this point, so I'm not going to change that. Okay. And now let's see if we're getting the same warning or something else. Undefined name wrapper. Would this be part of... It's not part of the instance, so we wouldn't use self to access it, and we couldn't even use self to access it. Like, how would we access it? Like, we're inheriting it. Do you inherit the static method with it? That's where, like, I like mildly tried to work this out previously for like, I don't know, 10 or 15 minutes. And it just didn't, it wasn't going where I wanted it to go. Like, I want a class that I can just like add to the inheritance and then wrap something with a decorator, and then all of a sudden it has like debug methods in it that just like everything that gets sent into method gets printed, the output gets printed, and it's just because you add this decorator. And then you take this, after you figure out you know, what's going on and you're done debugging, you just get rid of the wrapper, you get rid of the debug import. Just like, it just would be helpful once in a while. It doesn't really do anything outside of that. I'm gonna run this though just to see how broken it is. Yeah, because wrapper is not defined. And it's a static method, but it has access to the class. I mean, that's not going to work. You wouldn't even need to inherit it at that point. Yeah, this is just, I'm just like trying stuff to see if I can get this to work, and it is not playing along. Okay, I do want to see if we can change the static method definition of it, though. Okay. Let's get rid of that. And then this wrapper equals static. So this comes after the decorator. So maybe that's actually important to it. Let's make sure we're running again. Yeah, we are running again. Okay. Now, I'm wondering if I can just decorate this thing as a static method. Because it doesn't have the self. Like, there's no self here, so it's not part of the instance. And I wonder if that serves the same purpose. Okay, that works as well. And if it wasn't a static method, then it would have to have a self. I'd have to have an instance variable. And that wouldn't work because you use it here when there's not an instance. You use it while the class is being defined. But this does work. It's just like I want to inherit it from somewhere else. I wonder if we can access an inherited static method. So, see what I can find about that. We're going to leave that notebook alone. Let's see here. So, okay, I'm unclear on what is the best way to design a class with static methods that are meant to be overridable. I mean, you don't need a... I'm looking for something that would be... I mean, when you inherit it, it could be overwritten. So, the goat has a static method, can climb, and then I'm assuming they're going to inherit... Yeah, so they're going to inherit the mountaineer goat. And they're trying to overwrite it with another static method. Code that calls goat can climb knows that Billy is an instance of goat. It makes the assumption that its type is goat. Definitely not exactly what I'm trying to do here. Okay. Inheritance clearly means a knowledge of the base class. Static method is ignorant of the class it is attached to. Hence, they earlier, not nowadays, called it unbound. Now, technically, static method is not a method at all. It's a function. Yeah, I mean, static method is just like having a function outside of your class normally. Let's go back to the code. So, yes, normally, like you would just have this function outside the class because we're doing it as a static method. But if I grab this and I put it out here, can I still decorate the item in my instance? If I can still decorate it with this, then it just works. And I don't see, even the error went away. It's actually kind of weird. And that just works. So that actually achieves what we want, because we could call this something like log function method calls. And then we could make it just a little bit more complicated. Just give it some value z. I just want to pass something into it. And now this log method calls would say something like function called with inputs and then list the inputs. So this is going to be an f string func.underName called with args kwargs and then I don't actually need to do anything afterwards, so that's fine. Actually, yeah, I do. I want to log the output. And we can just say it returned output. And then it actually returns the output. So now we have this wrapper that we can put around any method, and it'll log what it's called with. This z should just be a value. And we can display z as well. So that might work. So now we have this method called with args 9. So args, of course, is just a list of all the positional variables, and kwargs is all of the keyword arguments. We could just add another thing here. So we can just add another one here. And just call it with something else. Just so we can actually see like some keyword arguments that are being passed in. And that should be that. I did see this cool thing in Python where this represents the end of the positional variable, so everything that comes after it must be a keyword arg, so that shouldn't change anything. Kind of like that a little. And I don't remember what the slash does. You can also put the slash in here. It's something very similar. It's like everything after this will be a keyword argument, something along those lines. So this just works. So I think we're good. I don't think we need to actually keep messing with, yeah, because it returned none, and maybe we want this to return something. Just anything, doesn't really matter. And Z is not part of the instance. Okay, so now we can see down here we have our method called with args, kw args, and then I wanted to include date time. So now we can see, we can add the date time to this kind of this logging function here. And we'll just print it right here. Built-in method of now object. Did I not put the parentheses there? No, I didn't. Okay. Okay, so now we have this info at a certain date and time. Method was called with args, and then we see the arguments that we passed in all the way from down here, and then we see the keyword arguments that was passed to this method, and then we have this, we still have this logging thing. So then the method actually gets called, and then we log out the return type. Yeah. Okay. So we have the decorator now. We have a decorator that is defined outside of the class object that can be used to wrap a method, and it has access to everything inside the instance. This is just an example of making like a logging method that would just display the time that you call the function, the arguments that were passed into the function, and the output of the function. So this could be really useful if you're trying to do a little bit of debugging or something. But yeah, it's just it's a cool little tool. But yeah, that's it for that one. So we're definitely done with this. I think it's time to take a look at a LeetCode challenge. And maybe it's just going to be an easy one. so let's try an easy LeetCode challenge first. Super user-friendly here. All right, this is the easy one. That's just cheating. We have to clear the old solution out first. Okay, so we have two special characters. The first character can be represented only by a 0. The second character can be represented by either 1 0 or 1 1. Given a binary array of bits that ends with a 0, so it always ends with a 0. Oh, because if it ended with a 1, you would know that it was this character. So it has to end with a 0, or else you know it's that character. Return true if the last character must be a 1-bit character. So I think we just step through this thing like 2 bits at a time. So we check the first value. If it's a 0, we move forward 1 position. So we can just step through this thing. And then if it's a 1, we can move forward 2 positions. Okay. And always control S-ing from LeetCode, which does absolutely nothing. Let's see. So, yeah, we just want to loop over this list of integers, which are going to either be a 1 or a 0. And we can use a while loop for that. So we'll start at the first position. And while I is less than, I know we're going to do the length of the list, but we may need to modify that just a little bit. And if the current bit is a 0, I plus equals 1. So we move forward one position. Whenever the bit that we're looking at is a 0, that means we have just this 0 character, or we have just this character, which is represented by one bit, so we move forward one position. And the only other thing it can be is a 1, so we're just going to use else. Plus equals 2. So then we move forward 2 positions. And now the only thing I'm concerned about is when we get to the last character, what actually happens there. So what we want to do is we're tracking the output for our last character, and it's going to be true if the last output. So given the binary array bits that ends in 0, return true if the last character must be a 1-bit character. So the way these things are stacked together, this character starts with a 1, so it must be this. So this is our first character. These 2 bits represent the first character. So the last character is just this trailing 0. So it ends with a 0, so we return true. So this returns true. And we could just put an output here. And then output equals false. And then just return the output. And I'll think about this for a minute before running it to see if it's actually correct or not. It may or may not be correct. But let's take a look. So this will work. Let's see. How would it treat this first example? So we're iterating for the length of bits. I is going to go, well, as long as I is less than length of bits, because the very end of it is where it's going to exit. So it'll only look at the last character, and if the last character is 2, we should hop over and be outside of this. Like, not only should we should actually exceed this by 1, is what I'm saying. Okay. And so we could actually just probably do a comparison down here to the I value. No, because even if it's 1, it's always going to end up exceeding the length. But this output true false thing may work. Like, we can't just look at the length I, because it's always going to be, yeah, it's always going to be this. Like, it's always down here, I is always going to be equal to the length of the bits. Because there's not going to be a 1 as the last character. They stated that the very last character, like, this thing always ends with a 0, so we're not going to hit a 1 at the end and then find ourselves in position to do that. To, like, jump an extra spot past the end. It's just not going to happen. Okay, so this should work with the first one. We come in here, we have our first position, I equals 0. It's a 1, so we're going to end up hitting this else. So then I is going to equal 2. The output's going to be false. We go up here, I equals 2. The length is 3, so 2 is less than 3. Bits in the I position equals 0, so we're going to move forward one position, set the output equal to true, and I is equal to 3. And we go up to the top, 3 is not less than 3. We get out of here, we do output, and it's true. So this thing seems like it's going to work. I think it's time to run it. Let's take a quick look at example 2. So we have we'll come in with a 0. It'll be this else statement that's 2 characters long. So then we'll go back up to the top. It's 2. The length is 4. The bit at the I position, the 2 position is a 1 again. So it comes down here, it adds 2. And the output is still going to be false. And then this will be a 4, which is not less than 4. So it'll jump down here to the output and we'll return false, which is what we're looking for. So let's run it. And it works for these two test cases, from what I can tell. We have an error. Oh, it's just, I'm not doing Python things here. Another language on the brain. Okay, so that's an easy fix. Just have to capitalize my Booleans. Okay, so that seems to be working, and I don't see a reason that it's going to break, so we're going to try to submit it like it's the real solution. And we've done it. And apparently I did this one a few days ago, which is how I knew to go find it as an easy one. But this is a different solution than what I had before. So what did I do? So this worked. We're just toggling the output between true and false. So this worked out really easily. Let's go look at the previous solution. Did something a little bit different. And compared, so when I was saying you couldn't compare I down here at the end to get your result, that's when we were going all the way to the length. So we were doing while I is less than or equal to the length of bits. But if you subtract one off of it, then you actually do have some knowledge of what that last character is. And I took advantage of that in this solution. It's not something I needed to know for the solution that I just came up with. But this thing, actually, these numbers up here really don't mean very much. So this probably doesn't run very much slower. There's not really a reason that this runs slower than the one that, like, this beats 73%, and logically this actually takes longer probably because we're changing the value of output. But then we don't have the comparison at the end. But with this one, we're only doing the incrementing values here. We're not calculating the length every time we come here. So there's, like, this thing should actually run faster, and you can see it just ran terrible. Like this, in LeetCode, this performance metric here, it actually means nothing, like nothing at all. Okay. So yeah, this one is good. I do have another worse, harder problem that's probably worth looking at. And it's just from a couple days ago. We can check the balanced binary tree one, actually. This is terrible. I don't remember how to solve this. And we already reset it. That's good. Actually, I need to go reset this one because I'm going to end up doing it again. Okay. Before we move on to the next problem, I want to give you, is there any questions out there? I just want to open it up. I don't know who's watching, but if there are just general Python questions that you have, or a question about the solution to the challenge problem that I just came up with, you're welcome to ask. I'm just going to wait a second, and then we'll move on. Okay, looks like we're good. Let's go find, yeah, okay. Everything's working. Let's go take a look at this worst problem, which involves binary trees. And it's always kind of nice to just uncomment this tree class. So this will be defined in the LeetCode system whenever you run it. But it's always nice to go take a look at this. So every node is an object. So tree node is its own class. Every node is an object. It's going to have a value. In this case, it's the first node has a value of 3. Okay, and then there are left and right values from the node 3. And over to the left, we have another node. So you can see that this left value is set to none by default. So it just assumes by default there is no value to the left. But in this tree, we have a 9, and to the right we have a 20. So this value, this self.right will actually be equal to, it won't be equal to 20, it'll actually be equal to another tree node. What you can't see here is that these are tree nodes. So like this value is going to be an integer. This left is going to be a tree node. And this right is going to be a tree node. And this actually creates a circular input, so, or circular import. So you would have to take some extra steps to define it like this, but that's not really necessary. But it's just like this left and right is another tree node. It's kind of like using pointers in a language like C++. But yeah, so this left is a tree node. And that's another object. And this right value is a tree node object. Okay. So that's how they're going to be connected to each other. And then, of course, below the 20, we have a 15 to the left and a 7 to the right. And if you look at the way they define this, they put them in a list, which is pretty confusing at first, but it's just left to right down the different depths of the tree. So you go 3, and then you go to the left side, 9, 20, and then over here to below the 9, there's no value, so it's null, null. And those aren't even like Python nulls, which are defined as none. But they're just kind of showing you how to define it as a list. But then we have finally the 15 and the 7. But what we want to do with these tree nodes and this tree node type is we want to determine if it's height balanced. And it's kind of important to consider what a height balanced tree even is. So they say a height balanced binary tree is a binary tree in which the depth of 2 subtrees of every node never differs by more than 1. Which sounds a little bit confusing, but so every node has a subtree. Over here, the entire subtree is the 9. And then over on the right-hand side, the entire subtree is this 20, 15, 7. And the depth of this tree has 2 layers of depth. And then this subtree, the 20, 15, 7, basically is 2 layers deep. And this 9 is just 1 layer deep because it's just one node, right? So this thing is balanced at the 3 node. So this has a depth of 1, this has a depth of 2. So far we're balanced, but you also have to check at every node. So you would check the 9, both sides have a depth of 0 because there's no children. So that's good to go. The 20, both sides have a depth of 1, so that's good. The 15, of course, has nothing underneath it, and the 7 has nothing underneath it. So these are both height balanced as well. So this example is a height balanced tree. And this is different than a complete tree. So a complete tree is full from the top down and then the left to right. So like this would not be a complete tree because it has these empty spots over on the left-hand side. On a complete tree, you're expecting to fill every layer before you go deeper and from left to the right, essentially. Now here we have an example of something that is not a height balanced tree. Down here at the bottom, the 3, this subtree down here is height balanced, and even this, the 2, like this left side of the 2 has a depth of 2 and the right side has a depth of 1, so it's balanced here. But when you get to the 1 node, this thing is no longer height balanced here because the depth on the left side is 1, 2, 3, and the depth on the right side is just 1, and that has a difference of 2. And you're only allowed a difference of 1 when you're trying to find out if it's height balanced or not. So that's actually not going to be a height balanced tree. And what we need is we need a way to dig down into this tree and keep track of if the current node is height balanced or not, because we want to know. Like if we were to get down here to this 3 and this thing was not height balanced, we want to immediately exit. So we want to we're either going to recursively or use a loop to dig down into the tree. And we probably have like a breadth first search or a depth first search option here. I haven't actually looked at doing it both ways. I believe I do depth first. So to me, like breadth first search would be you check the 1 and then you check this 2 and you check this 2. But that doesn't really work because you haven't gone through the entire depth of the tree yet. So you would end up going all the way down. If you're doing breadth first search, you would have to check 1 and then these 2s, but you still can't check these 2s because you haven't hit the end. And then you would check this third layer, and then over here you would hit the ends, so you could technically be done with this piece, and you would know. Before continuing down. To me, what makes a lot more sense is to go depth first, and what that means is you just go you go left, 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 check this to the left, nothing, check this to the right, it's within 1, okay, it's nothing also, okay, this 4 is good. Now let's check this 3, and then when we go back up from this 4 to the 3, we have to be returning the depth. So like the maximum depth of this 4, like we want to return it back up. So maybe we return a 1. So like with this 4, it has a depth to the left of 0 and a depth to the right of 0. And then when we return a value, we want to tell this 3 how deep down we went. So we've got to say, return the depth of 3, or return the depth of 1. So we do want to return the depths of value of node being checked. Okay, so we do want to return the depth of the node being checked, because once we go back up to this 3 after checking the 4 and knowing that it's good, we're going to go to the right side and we're going to check this 4. And when we hit this 4, we go to the left side, which is nothing. We go to the right side, which is nothing. We know that this 4 is balanced, and we return a depth of 1. So now when we get to this 3, we're going to have a depth of 1 from the left side, a depth of 1 from the right side, and then we're going to check those two depths and compare them to each other. So what we're going to want to do is get depth to the left side. Say like left, or the left side, and yeah, we don't know what that's going to equal yet, and this is going to equal something. And now if what we're trying to do here is we need to make sure that these are balanced, so the left depth and the right depth of any node needs to be within 1 of each other, and we can do that with an absolute value. So if the absolute value of right depth minus the left depth is greater than 1, we're going to return something. But the problem is that we're returning these integer values. So whenever we're down here, we're returning the depth of this. So we don't want to, we're not returning true or false. We're not returning a Boolean. So normally we would return false, like this thing is bad, right? We want to return that this is false. And what we're doing here is a depth first search. So let's go ahead and define that. And this is going to be something. Like we don't know where we're going to call this and how it's going to work exactly yet. But we are going to be doing a depth first search. And this is going to have some sort of node that we're checking. So we know that if this difference is greater than 1, we're going to return something. We want to say this is bad, because when you're all the way down here and say that this 4 was unbalanced, which it's fine because it has no nodes, but let's say that there was like 5 nodes on the left hand side of this 4. This 4 would not be balanced. So we want to return something that tells this I'm already not balanced, because otherwise you're going to check to the right side. Like if this 4 is not balanced, we want to tell the parent node that we're not balanced. Otherwise it's going to check the right side, and then it's going to check every other node. You don't want to check this whole tree. Like as soon as we know we're not balanced, we want to return values all the way up and say we're not balanced. So I think the thing to do here is to return the node depth or -1 if not balanced. Wait, so return node depth if balanced. And what's the actual term? It's not just balanced, it's height balanced. And that's actually going to be tree depth. So return the tree depth if it's height balanced. So if this 4 is height balanced, the total depth of this tree, subtree down here, is just 1. Okay, so we're going to return the tree depth if it is height balanced. But if it's not height balanced, we want to return a -1. So we're never going to have a tree that's, we could have a subtree that's depth of 0. So if there's no nodes, it could just return 0. But we're never going to have a depth of -1. So instead of returning false, we want this whole thing to be, integer based. So it's always going to return an int like this, because we don't want to return 0, 1, or whatever the depth is, and then also return false whenever it's bad, because that's just weird. Like then you're going to be checking an integer value to see if it's false, and that doesn't really make any sense. So right here, after we get the left and the right depth, so in order to get the left depth, what do? So we need to branch off and do a DFS on the left node. And in order to get the right depth, we're going to do node.right. Okay, so now we're checking to the left, we're checking to the right. We need to check if either of these values are -1, and then immediately get out of here if it is. And there's no reason to even go down the right side. We want to check this immediately. As soon as we do the left side, we check and see if it's not balanced. Because if this is not balanced, we want to get out of here. And we're going to return -1. So these things are going to chain all the way up. So if we go all the way down the left side, we find a negative value because this, let's say this 4 is unbalanced for some reason. It's going to immediately return back up. It's never even going to check the right-hand sides. It's going to save us a ton of time. And then we want to do the same thing on the right-hand side, because if like this 4 over here in the middle, or to the right of the 3, like if this thing was unbalanced, so we come all the way down here, the 4 is balanced, we go back up to the 3, we check the right-hand side. Now this is unbalanced. We want to go back up and just exit immediately. So same thing. So if the right depth is -1, we're actually going to return -1 from here. Keep trying to save out of instinct. Okay. And now that we've checked to the left, if it's bad, we return. We've checked to the right, if it's bad, we return. If the difference between the right-hand depth and the left-hand depth is greater than 1, then we know that this is bad. So we're also going to return a -1 here. Otherwise, we're going to return the depth of the tree, of subtree. And the way that we do that is, let's say we're at the 3. When we return from this 3, we want to pass a 2 up here. So from the 4, we're going to return a 1, because the total depth of this subtree over here is 1. And we know that because the depth of the left-hand side is 0, and the depth of the right-hand side is 0. So there's two things that we have to handle here. We need to handle the none case. We haven't done that. We come into this function, and we immediately try to access the left and then the right-hand side. We've never checked to see if this node is none. And if this node is none and we try to go left or right, it's going to say try to access attribute of none type, and that's an error. As soon as you start working with these tree and graph structures in Python, you will run into that error. It's bound to happen. So let's just handle it here before we even run into that error. So if node is none, return 0. And again, we're returning the depth, right? So when we go down to this node here that doesn't exist, it has a depth of 0. So we're checking this, we're basically, like this node to the left of 4 has been passed in here because we're not checking it before we pass it in. That would be the other thing. Before you call this function, you could check if the left and right nodes are actually none, and you could just set this 0 equal to 0. So you could say like if node.left equals none, left depth equals 0. I'm choosing just to do the pure recursion, so we'll call in here, and then we'll have this exit condition to get out of the recursive cases. Okay, so we've done that, and now we need to return the depth of the subtree. And it basically needs to be the maximum depth of the subtree, so it's going to be, like if we're at the 4, it's 0, it's the length on the left is 0, the length on the right is 0, and this is 1 deeper. So let's take the max of left depth, right depth, and we're going to add 1 more to it. And that's the depth of the current tree. So if we were at this node 3, like the length of this thing on the left is 1, the length of the thing on the right is 1, we're going to take the max of the left branch and the right branch, and we're going to add 1 to it, which is 2. So now here, we're going to tell this, at this layer, we're going to say the subtree to the left is 2 nodes deep, because we did 1 plus 1. And then we'll check the right-hand side of it. This will go down 0 plus 1. The depth of the right subtree is 1, and then we'll actually compare them to each other. So absolute value of 2 minus, actually it's we did right minus left. It doesn't really matter, but I would prefer just to do left minus right, just for the way that it's kind of written, and everything else is like that. But yeah, so we're going to do like depth of 2 minus 1, and then take the absolute value, because you don't know which side is longer. And that difference is not greater than 1, so we're fine. And then we're going to return the max of the left depth and the right depth. So the left depth is 2, the right depth is 1. So we're going to return the value of 2 plus 1. So up here, you get up here, the left-hand side of this thing is now equal to 3. And we check the right-hand side. It goes here, it checks left and right. You get zeros, it returns a depth of 1. So here, the depth of the left subtree is 3. The depth of the right subtree is 1. And we're going to check that right here. And when we take that difference in absolute value, so it's going to be 3 minus 1 is 2, and that's greater than 1, it's going to return a negative 1. So we don't actually find out that this thing is unbalanced until we get back here to the root node. So it takes a pretty long time. And we could look at, for this same example, you're going to start here, pass in the first node, and then go to the left. It's going to have 0 depth. So this is going to return 1 depth. We're going to go to the right. It's going to check left. This thing comes back with as balanced and a 1 depth. The 7 comes back as balanced and a 1 depth. The 20, it compares the 1 on the left to the 1 on the right. This thing has a depth of max of 1 and 1, so plus 1, and so it returns 2. So the depth on the left is 1. The depth on the right is 2. We have 1 minus 2, take the absolute value, and it's not greater than 1, so it's going to keep going, and then it's going to return the maximum depth of the left and right plus 1. So when we get done here, it's going to return this value, and we're actually going to get a 3 because the maximum depth is 3. So we still need to finish this function off and apply some sort of logic. So what we need to do is we're going to call the depth first search, and we're going to pass it the root. And even if the root is none, you can see that this root is an optional tree node, so this root could have a none value. It's just going to come back with a 0. And inside of this, this is balanced. It needs to return a Boolean, and right now we're just calculating an integer value, so that's really not what we're looking for. So we're going to return this, which is not going to be an integer. Let's just compare it and just say greater than -1, because if it's -1, we'll know that it is not height balanced, and that's going to be false. If it is greater than -1, even if it comes back as 0, that is going to be balanced as well. So I'm assuming that they give us the third example right here. So they give us the empty tree, and it comes back as true. So we want to make sure we're handling that as well. So if we call depth first search with an empty tree, which is just going to be a none value for root, goes up here, node is none, it just returns 0. 0 is greater than -1. And now we're good. So this is true. So I feel like we can push the run button. Is there any any problems out there that I'm missing. I'm going to take a drink here, give you a second to look at this and kind of think about what we've done. If there's any problems I should fix before we press the run button, just let me know. All right, we are good. It's time to push the run button. With any luck, this thing will work. There might be... That is a first try. That definitely does not happen very often. Okay, so it worked in all three cases, and we were pretty careful about how we went through it. And I think this might be exactly how I solved it the other day when I first did this problem. So I've done this problem recently, which makes it nice and easy to talk about without having to struggle so hard. But now let's push submit and see how it performs against the rest of the test cases. Okay, so it worked against all the other test cases. So I did this on the 21st, which is about 4 days ago. And it looks like I did it wrong a few times. And that was mostly because, we'll take a look at those other results. But I had the height balance. I was trying to check for a complete tree, which means that the left side is filled up before the right side and that there's only one layer of depth difference at all. So you can only have one layer on like you fill up the rows from left to right for a completely balanced binary tree, or what's called the completed binary tree. So I was checking for a completed binary tree. By this one, I probably had it worked out really well to check for the completed binary tree, and it was not working. And I looked up the definition again and was like, oh, that's not what I'm checking for. So this is the one that we just submitted and ran. It actually worked first try, which does not happen very often. Even when I go back and revisit these things, there's typically, there would be an error somewhere. But I got a feeling this is very similar, if not the same, to what I did before. So let's just take a look and see if there's any difference here. So depth first search, I even had the typing here. If node returns 0, and then I checked for the -1. Or I said equals. Yeah. So I just had LD for left depth and RD for right depth. So I had a little bit shorter variables. And then, again, absolute value. I did the right minus left, but I didn't switch those when I didn't look at it. And then I put an else statement here. And then instead of, the only difference I'm seeing here is at the end of this, I did the logic directly here. And on this one, I did the classic, like, programmer, if this is true, return true. If this is false, return false. This is actually kind of a meme. So this thing gets joked about on Twitter quite regularly, where this is like the more like programmatic way to do it, because you already have the logic there. You don't need to check to see if it's the logic. You just straight up return the value. So we did improve the solution from 4 days ago. All right, I got one more, and it's actually a hard problem that I solved yesterday, maybe earlier today. I'm not even sure. But I want to take a look at this one, because it's a hard problem, but it was actually, as far as hard problems go, it was pretty easy. So let's take a look at this problem first. And yeah, usually when I see the hard symbol, you know it's going to be a bad time, right? So we are given an array of distinct positive integers, which are locations. So we have this array locations, and they are distinct positive integers, so the value will never be the same. So each one is just different from the other. And these represent the position of the city in the ith position. So the index that we're using to reference locations is I, and it just represents a city. We're also given integers start, finish, and fuel, representing the starting city, the ending city, and the initial amount of fuel that you have. So at each step where you're in city I, you can pick any city j such that I and j are not equal to each other. So you can move from one city to the other. That's what this is saying. And then, yeah, you go from city I to j. Moving from city I to j, you use the amount of fuel, which is the absolute value of the difference between the two locations. So you take the location at I, the location at j, subtract them, and then take the absolute difference, or the absolute value, and that's the amount of fuel that you use. And then we'll notice that fuel cannot become negative at any point, and that you are allowed to visit any city more than once. Okay, so you can visit a city more than once, so you are allowed to go to a city more than once. So this is not the traveling salesman problem exactly. So the traveling salesman problem is what's the optimal path to go visit every city. So this is kind of similar, and what we're going to do is we're going to return the count of all possible routes from start to finish. And since the answer may be extremely large, return modulus of whatever that is, 1 billion plus 7. So, okay. So this is a search problem again. So we are going to be performing some sort of search, but they give us kind of an easy example, which is just, I mean, we have these individual values, but we only have 5 fuel, and we're starting at 1, and 1 is the index. So you see there's no value 1 in here. So we're starting at the 3, and we're finishing at the third index, which is 8. So you can go straight from 3 to 8. That's 1, and that uses 5 fuel because the difference between these is 5. You could go to the 6, which is a difference of 3, and then to the 8, which is a difference of 2. So again, 5 fuel. And then you could go from the 3 to the 4 to the 8. Yeah. So you go from 3 to 8, that's one method. You could go from 3 to 6 to 8, that's what this is. You could go from 3 to the 4 to the 8, that's valid. But you could also go from 3 to the 4 to the 6 to the 8 is what this final one is. So they're saying, so 3 to 4 is 1 fuel, 4 to 6 is 2 fuel. So you can see you could actually go in order, like you could go up the sequence of these things. And that's like completely acceptable, and that seems like it might lead you to some sort of solution. And maybe it does, but that is definitely not the way that I would do this. So the way that I'm looking at doing this is, again, a breadth first search, or a like a search technique, but probably breadth first search. The previous node example here, we actually did a depth first search because we wanted to go all the way down the left-hand side first. But on this one, we're kind of looking to burn up all the fuel. So maybe I want to go from my starting node to these other ones and then check if I'm at the final destination, increment that I've arrived. And then from each of these nodes, we want to again go and travel to all of the other cities. What's kind of weird is we're starting at this, this 3, and you can go back to it. So we don't have enough fuel to do it. But if we had more fuel, and you can kind of see that down here, but we could go like 2, 3, and then over here to the 8. And that would require 7 fuel. So we would use 2 fuel to go to the 2 and back, because there's a difference of 1. And then we would use the 5 fuel to get over to the 8. But we don't have enough fuel to do stuff like that, so we don't actually see that pattern here. But we do down here. So we're starting at the 3, and we're trying to get to the 4. But we have 6 fuel. So we can actually do things like go 3 to the 1, that burns up 2 fuel. back to the 3, that's another 2 fuel, so we've used 4 fuel at this point, and then we can go over here to this 4, and that's at the finish, and we've used 1 more fuel, that's a total of 5. So this is all very reasonable. So whenever we're doing our search, we don't have to keep track of the nodes or the cities that we've already visited. And that's the important step here. So normally when you do these and you're traversing different graphs or you're checking out different paths, you're tracking if you've already visited a city or not. And we don't have to do that because we're allowed to visit the same city. And not only are we allowed to visit the same city, but we're allowed to visit the finish. So you can see that we have multiple zeros here, and 0 is the finish. So we can go from 3 to 4, back to 3 to 4, and that's what this represents. So we go from position 1 back to position 0 to position 1 back to position 0. So we've actually visited the finish twice, and this is just one more route that we could take to end at the finish. It's actually kind of bizarre that we're allowed to revisit the finish, and it makes our graph much worse because you don't stop. Like when you get to the end, you don't stop. You keep going until you're out of fuel. So we're going to try to do this recursively, and we're going to see that there's just too many options. So we'll have to find a way to approach that. But first, let's look at doing this with a breadth first search. Okay, I'll display the problem, and then we'll take a look at some of it. So we know we're doing a breadth first search, so let's just define BFS. And then we know, so within this function, so by defining this function inside of the other function, we just have access to everything. And we're going to return, what are we going to return? We're probably going to return a count of the total paths to get to the end of the city, right? So we're going to return a count of all possible routes from start to finish. So we're going to return an integer. So we're keeping track of how many. And we can probably just keep track of our paths here. And routes. Something like routes equals 0. And then down here at the end, return routes. And we're going to have to take the modulo. So down here at the end, they say take the modulus of this thing. And we'll use a few underscores. And 7. So they're saying 10 to the 9 plus 7 is what they want us to take the modulus, because this number could get huge. And the question is, are we going to be adding these routes up as we go? Maybe. So let's see. We are going to be adding these as we find more and more routes. So I don't know if it's happening here or if it's happening in the code somewhere. But what we can do is use our city here. So we can have our start location. We can either use the actual start, or we could use I. So it looks like we want to start at I and then go to J. And we have access to all of these values here. So we have access to, because we're inside of this count routes and the way that Python works with the scope of these variables, we're going to be able to access locations. We can access start, finish, and fuel all from inside of here. And we don't have to do anything else. Okay. And I think we're going to be passing around the fuel, because that's going to change every time we take a route. And we're going to pass in how much we have remaining. So if we're ever out of fuel, if fuel is less than 0, this is less than or equal to 0, just return routes. And that just means, so we can't go any further. So here we're just going to return 0 because we know that we're out of fuel. Okay. But now that we know that we have some fuel, we can check some things. But first, let's actually call this function, because we haven't really said what I is, and we want I to be start. The first time that we call this, we want to start at our start city. And then we're going to branch out to all of our options, You can't go from the start. You can't go from the start position to the back to itself. But we can go to every other city. So let's do our BFS. And we're going to go from the start. And we're going to pass in the fuel. And now we're going to check for all of the other locations. And if we're at the, let's see, so we're going to iterate for all the places we could go. And it doesn't even matter if we're just going to go there, right? Yeah, we're just going to go there. As long as j is not equal to I. So if j not equal to I, so we don't want to start and end in the same city. So we never want to do that. So you can't take a trip to the city you're already in, is what this says. So if j is not equal to I, then we can actually do something. Now, if j is the end city and we know we can get there, we need to add this. We need to add 1. Is this where we do it? Let's see. What about... we could... Is this where we want to check? Because every time we get to the end city, we want to increase the route. Do we want to do it here or do we want to do it here? So if we get to this part of the code, if we get right here, we already know that we have fuel left. Say if it's less than 0, because you can get to the end city and have 0 fuel. So we do need to change that back. So now we know we made it to this location. We made it to I. Whatever this is, we made it here, and we at least got there. We didn't run out of fuel. But if I is equal to finish, we want to increment routes. So we can add 1 to the routes. Yeah. And then even though we're here at the finish, we can keep going and exploring other routes, because you're allowed to be, so we've identified 1 path to the finish, and now we can keep searching, because we saw in the second example, even though you got to the city, so like this pattern happens, we add 1 to the path, but then we're still here, we can keep exploring. So we would end up finding this and this. So we would find the second one, and then that matches this pattern, and we would keep exploring, and then when we got here, we would actually add a third. So these 3 paths are going to be kind of all part of the same search part, and then this other one will be a different branch down here. But yeah, so this will work, and the only time that we want to continue exploring is if j is not equal to I. Then we're going to continue exploring with BFS, and we're gonna travel to j because that's where we're going, and then we need to update our fuel. So we want to have our fuel, and then we're going to subtract the absolute value of the location I minus the location of j. Right, and the absolute value, so it doesn't really matter what order we do these in. And we know that because they tell us over here the amount of fuel to travel locations is the difference, and you take the absolute value. But this is going to return a value. This is going to return something. And we want to add to it, right? So does that mean routes plus equal this? So if we travel to a new location and it ends up that we find the finish again or multiple times along those routes, we want to add, and we're going to return all those things, and they're going to accumulate. And when we finally return it out of the BFS, we're going to take the mod, but we're going to keep adding them up within here while we explore all the cities. So this is the BFS part. This is where we're actually branching out to all of our neighbors. This is the breadth first search. And it may actually execute like depth first. That might not actually be right. We could probably call this depth first search, because I think it does get all the way. It will actually go. So it'll be like J equals 0 until you run out of fuel, or J. It probably is depth first search, honestly. Breadth first search is a little bit weird. Okay, but that's not really what we're concerned with here. I think we just want to run this, but I do want to think about it for a second before I push run, just because it's good habit. So we're going to have no routes when we get here. We're going to send in the start. We're not going to have any routes. If fuel is less than 0, we're going to leave because we're out of fuel. If we made it to this location I and it happens to be the finish, we're going to increment the routes because we found one route to the finish. And then we're going to check to see if we can keep going. So we're going to iterate over all other indexes, which is 0 through the length of this thing minus 1. Oh, we have to do the length here. Yep. That's an error. So we have to take the length of the locations. And since we're doing this, since we're doing the range of this to get the index, and we're actually using the location value, let's do a little bit better Python here and take j, loc j in enumerate. And we're going to enumerate this locations. So now instead of location j, we can just do loc underscore j. And then we can get rid of this one if we want to, but we don't have to. We could just say loc I equals locations I up here if we wanted to. But yeah, so now we no longer have to reference this because we're just enumerating over all of the locations anyway. Yeah, that still looks like it works. And I'm nervous about this, but we're only adding one, really. So we're adding one at a time. It's equal to itself plus all of the additional routes we find here. So it's only ever being incremented while we're at the finish. And just every time we pass by the finish, this BFS should go, we changed that to DFS. This DFS should go up by 1. And then we return the mod, which is just part of the problem statement. I'm going to push run and see if there's errors, because it looks like it works. If this doesn't work, I don't know what I'm going to do. It does. Okay, so it works. So that is a heck of a good start. And now I think it's time to just test it with other cases. So we didn't even look at the third one. But yeah, it just has 3 fuel, and there are actually no ways to go. So we start at the 5, and we try to finish at the 1, and we only have 3 fuel, and we just can't get there. So we got a 0 out of this. So start, finish, fuel 3, output is 0. So it just, even when there's no paths, we got the right solution. So at this point, yeah, I know it's not going to work because this problem blows up, but I am going to push submit so we can see how it blows up. Is it going to blow up? Is it working? Hard to say. What is happening? Okay, time limit exceeded. So it ran out of time. And that's because this problem is insane. So as soon as you have more fuel, and what happened here is we have this short path. We only have locations 1, 2, and 3, which seems very simple. Like, why did we run out of time? It's because we have 40 fuel. And we keep checking all the different combinations. So we start at the 1 and we end at the 3. So we go from 1 to 2. and then we go from the 2 to the 1 to the 3, but when you're back at the 1, you go from the 1, and just like, it's all of these different combinations. And what we need to do is something from dynamic programming to use a technique called memoization. Because we don't want to, this fuel value is only 40, and we only have 3 different locations. So there's not really that many combinations from 1, 2, and 3. So this, if you look at the inputs of this function, it's going to be either a 0, 1, or 2 for the index of the position. And fuel only goes down. So fuel will be like some negative number, which would be like -3 potentially if we call this in a terrible way. So -3 all the way up to 40. So we really only have like 44 different values for fuel. So we've got 44 different values of fuel and 3 different values of locations. Otherwise, and then we know every possible result of DFS. But this thing is actually calling it many, many more times because we permutate all the locations each time we move. So we want to do this and use memoization. And normally I just do cache. So I'm going to do it the hard way just for the sake of recording it. But I'm going to show the cache. Cache just memoizes a function for you, and it's part of functools. So cache is a lightweight, unbound function cache, sometimes called memoize. So LRU cache is like a limited size cache. So if you only want to take up a certain amount of memory, because your cache can exceed the amount of memory you have, and your program will run out of memory if you do this wrong. But all you have to do is put the decorator above the function and just say add cache. So if we want to cache this thing, all we have to do is that. And now this function is memoized. If we've already called it with, say, location 0 and fuel 40, I mean, that is the final version. That doesn't really make much sense. But if we call it with location 0 and fuel 3, which will happen over and over again because of all the different combinations of ways that we subtract fuel off, it's only going to evaluate it one time. Once it knows the answer, and there will only be one answer, it's just going to store that value in memory. And then when you call it with the same numbers, it just pulls that value out of memory and then returns it. So this will run much faster because it cuts off the recursion. You never evaluate this function with the same inputs more than one time. Every time after the first time you call it, you just return the value from memory. But the way you do this manually is usually with a dictionary. And I think tuples are hashable. So if memo.get I comma fuel is not none. So if the value already exists, then we're going to return, let's see, wait. Yeah, this is fine. So then we pass it, then we just return the value. So if it's in the memo, we just return the value. But if it's not, then we calculate the normal value. And then we can just set the value here. Hopefully this works. I haven't actually tested this. I'm a little iffy about putting this tuple in the dictionary, but I think tuples are hashable. Let's find out. Boom. Right there. So immutable objects such as tuples are hashable since they have a single unique value that never changes. So that's why we can do this. So in order to do something with a dictionary, this has to be hashable. And then we just return this value because that's what we just did. And in fact, since we've already checked that it's there, we don't have to use the get function again. We can just return that value. So let's run this again without submitting it just to make sure that we did not make any errors. So if it exists in the memo, we're just going to return the value. So if it's not none, whenever we try to get it, we return the value. If it is none, we still calculate it, and then we add it to the memo here at the very end, and then we return the value. So we should never perform the same calculation twice is what this does. So let's run it. Please work. Don't fail me. How are we doing? Okay, it worked. So now let's see if this is fast enough to not run out of time when we do the harder version. And if we were clever, we would have added that to the test case and we would already know if it works. But we did not add it to the test case this time. Okay, it worked. Outstanding. So you can see that we exceeded the time limit here. I had a previous answer. I thought I exceeded memory usage on one of these, but yeah. So on this one, we exceeded the time limit because we didn't memoize the solution, and the depth of this thing just goes insane. And you just get basically stuck in an infinite loop because it takes too long to find the solution. So we used memoization and we made it. But the previous way that we did this was using the cache, and that does the same thing as memoization. You don't have to bother with all the dictionary weirdness that got added to it. This is actually a much better, cleaner solution, and I highly recommend doing it this way. So I'm actually going to wrap it up on that third and final problem. So I want to thank the people that watched, and hopefully this helped, and we'll see you next time.